Everyone, hello. Thank you, Dr. Baday, for the introduction. Today, we are going to continue with our sessions on interview preparation on statistics. If you guys participated in the previous sessions, so we solved a couple of problems, like 2 or 3 problems per session. So that's what I'm going to do today. I'm going to solve one probability problem and then 2 A/B test related problems. Again, you don't need to you don't need any file. So you just if you like, you can code with me. So if you can just simply open your Jupyter notebook, or you can use Google Colab. So as I try to solve the problem, we're going to do the coding together. Okay. So let me share my screen with you, and anytime, at any point, please let me know if you have any questions. It's better if you post your questions on Q&A instead of chat. I may not see your question if you post a chat, because there are so many messages out there. So let me share my screen quickly. Just 1 second, please. All right, so sorry about this quick interruption. So again, please post your questions at Q&A. I will try to check your questions. And let me post the question on the, what is that? On the chat, so that you can have the question immediately, and then you can just copy and paste it if you're interested in, okay? All right. So let's say you have a bag of coins. X of them are fair. Y of them have heads on both sides. All right. And Z of them have tails on both sides. So we have a number of coins in a bag, and X of them are fair means when you flip the coin, there is equal probability that you can get head or tail. And then there is a number of other coins that they both have heads on both sides. So it's not fair, right? Both sides are. So in other words, when you flip the coin, the probability that you're going to have head is 1. The probability that you're going to have tail is 0. And there are Z of them. They have tails on both sides. That means the probability of that, it's opposite of the second one, right? So when you flip this Z number of coins, any of them, you're going to have tails on both sides. Okay. You cannot copy from chat. I don't know how we can make it you copy from chat, but let me see if there is any way we can make it copy. So I don't know. I cannot control whether you can copy it from the chat or not. Let me post it at Q&A, but I don't think you can copy it from there too. So okay, then the thing is, maybe you can simply take notes as you see the question. So sorry about that. So yeah, that's the distribution of the coins in the bag, X, Y, Z number of coins. So if you draw 100 coins at random from this bag, okay, so you draw a coin and then put it back, draw it again, put it back. So they're gonna be drawing coins from this bag with replacement. That is what with replacement means. You're gonna put it back. So each time when you draw a coin, you still have the same coins in the bag. So and then you draw a coin and then you flip it. Okay, you flip it. What is the expected number of heads that you will see? So this is the question. So the way we're going to solve this question is, first, mathematically, we're going to solve it in terms of X, Y, Z. And then maybe we can assign some numbers to X, Y, Z, and then find our answer based on our mathematical solution, and then we can simulate it. Okay, so that's what I'm going to do. Hopefully, it's going to help us understand the question better. Yeah, you can get it via screenshot, actually. Yeah, thank you. Okay, so let's think about this question. So we have, Y number of, so we have, let's begin with X, because X comes first. We have X number of coins. So what is the probability that when I draw a coin from this bag, I'm gonna get these coins which are fair? Okay, what is the probability that I'm gonna get one of these fair coins? It's basically X over the total number of coins in my bag, right? So X over X plus Y plus Z. So this is the number, this is the probability that I'm gonna be drawing a coin which is, what is that? Fair. So the same goes for the other ones. So the probability that I'm gonna draw one of those coins which have heads on both sides, it's Y over X plus Y plus Z, right? And then again, the probability that I'm gonna pick one of those coins which have tails on both sides, Z over X plus Y plus Z. All right. So now, so this is the probability that I'm going to pick a coin which is fair. So given I pick a coin which is fair. So what is the probability that now I'm talking about flipping it, right? Flipping it. So given I pick a coin which is fair. So what is the probability that I'm gonna get heads? So I'm talking about heads, right? So what is the probability that I'm going to get head if my coin is a fair one? So it's basically 1 over 2, right? Because this is a fair coin. So the probability that I'm gonna get a head is 1 over 2. Then I'm gonna multiply 1 over 2 by the probability that I'm going to, let me put this inside parentheses here, the probability that I'm gonna actually draw a fair coin. Right? So if I multiply these two, this is giving me the probability that I'm going to get head if I pick or draw a fair coin. So same thing goes for the unfair coins. So for Y number of coins, I have heads on both sides, right? So if I flip it, this unfair coin with both sides head, what is the probability that I'm gonna get head? So for sure, I'm gonna get head because both sides are head. So I'm gonna multiply this by 1. Okay, let me also take this inside the parentheses. Now, similar logic applies for the Z number of coins, but keep in mind that this time these coins have tails on both sides. So the probability that I'm gonna pick, when I flip it, the probability that I'm gonna have head is 0 because there is no way I can get head because both sides are tail. So if I add these guys together, so this summation of these 3 terms, 1, 2, and 3, summation of these 3 terms is actually expected number of heads if I draw a coin from this bag and then flip it. Okay, so this whole term, summation of these 3, it's actually expected number of heads if I draw a coin randomly from this bag and then flip it. But in the question, it says 100 coins at random with replacement. That means I'm going to be repeating this 100 times. It's basically, I'm just going to multiply this whole thing, summation of these 3 terms, by 100. So that would be giving me the expected number of heads if I have X, Y, Z number of coins with these different attributes, right? And then I draw 1 and then flip it and I repeat this for 100 times. So I think this might be the solution, but you know, let's try to simulate and then see what we found is actually is correct, and then correct me. Mistake on 1 over 2. Correct me if I am wrong. So where is 1 over 2? So this is the probability that I'm gonna get head if I flip a fair coin, right? So this is the probability that I'm gonna get head, and this is the probability I'm gonna get head for the unfair coins. Okay, so now let's try to test our solution. Okay, I'm just gonna give some random numbers. Okay, so let's say I have 20 of fair coins, and then what? Let's say 34 of unfair coins, which are both heads, and then what, let's say 13 of, again, other unfair coins, which are both tails. And then, as I said, n is 100. That means I'm going to be repeating this experiment 100 times. So let me assign these values to x, and then I'm just curious, what is the answer for this guy? It is 65.67. So the expected number of heads, if I have x, y, z values assigned as 20, 34, and 13, respectively, right? So the expected number of heads in this case is 65. Okay, so now, as I said, let's try to simulate this. Okay, let's try to simulate this. So there are many different ways you can do it. Again, mine is if you guys have a strong programming background, you can come up with a much elegant way of running this experiment. But let's do it this way. So I'm just going to say coins. So what I'm going to do is I'm going to label the fair coin, so with F, the coin with both sides head is with H, and the coin with both sides T as T. So what I will do is I will just create X number of F, okay, and then Y number of H, and again, this is a very simple simulation, and then Z number of T's. So basically, this is the coins in the bag. So if you just look at the coins, right? So these are the coins in my bag. So now I'm going to be drawing a coin from this bag randomly. So if I draw an F, that means I'm drawing one of those fair coins. If I draw H, that means I'm drawing one of those unfair coins with heads both sides. Okay. Now let's import a library called random. So because we are going to use this for randomly picking a coin from this bag. Again, my bag is the variable coins. And then I will also import from SciPy, I will import the uniform distribution. So there is a reason why I'm picking the uniform distribution. If you guys saw the previous sessions, we tried to explain that. I'll try my best to explain in here too. Okay, so let's create an empty list, and this list is going to be holding the heads. If it is head, it's going to be holding in this list. Okay, so again, I'm going to be drawing 100, I'm repeating this for 100 times, say for I in the range of n. So n is 100, okay? Okay, now we are going to pick one coin from my bag, coins bag. So let's say Z is a randomly picked coin. So I will use the command choice. So function actually, choice, which is going to be picking one coin. So let me show you how it is working. So import random, and then random dot choice coins. So basically, it's every time it is picking a random letter from this coins text. Okay, so string. Okay, so Z is our coin. Now, if Z is a fair coin, right? If Z is a fair coin, of course, it has to be. If Z is a fair coin, then now so I know that this is a fair coin. Now I am going to flip this. I know that because it is a fair coin, I'm going to flip this. Flipping means a 0.5 probability it's going to be head, and 0.5 probability it's going to be tail. So let's simulate that. So for that, I'm going to pick, sample a value from a uniform distribution. So that's why I used imported this uniform distribution. Okay, so I will create a random variable between 0 and 1, which is uniformly distributed. So imagine that you have a number line from 0 to 1, 0, 0, 0, 0.001, 0.002, all the way to 1. So any of these numbers between 0 and 1 has the equal probability of being picked. Okay, so that's what we are doing. So we are picking a number from 0 to 1. So what I'm going to do is, if this number is less than 0.5, I am assigning that if the number is less than 0.5, that interval from 0 to 0.5, that interval, I will assume it is head. 0.5 to 1, I will assume it is tail. So you can do the other side. It's not a big deal. It's the same thing. You can say that from 0 to 0.5 interval, I will assign it to tail. 0.5 to 1, I will assign it to head. Same thing, doesn't matter. The important thing is what percentage or ratio of that 0 to 1 interval you are assigning to head and tail. Here, 50% of the interval is assigned to head, 50% of the interval is assigned to tail. What you can do is from 0 to 0.2 tail, and then 0.2 to what? 0.7 to head, 0.7 to 1 tail again. Again, it still works, okay? So again, we are doing this very simple. From 0 to 0.5, I will assume that if ZA is 0.5, I will assume that I flipped the coin and I got heads. So I will append, let's do capital H. That means I'm just keeping H, capital H in the heads empty list. Okay, so again, this is if I picked one of the coins which is fair. Well, I had two other types of, what is that, coins, right? So if, else if, right? Z is H. So this is one of the unfair coins. I know that if I pick H, both sides are head, so definitely it's a head, right? So heads dot append head. Okay, now else. So else means, well, I am going to be picking unfair coin which has both tails. Then there is no head, right? So I will continue. Continue means I will just I'm not gonna do it, so I will do anything, and then I will just continue iterating in my for loop. Okay, now let me print the length of my heads. Again, remember, heads is only keeping H if it is head, okay, when I flip a coin. So some print is missing here. So it came 66. So mathematically, we found it's 65.67. Well, I can run this. So here, I can run this many times. As you see, because it is expected number, right? So it's not certain. Because there is probabilities involved here, it's going to be 66, 64. So then you may wonder, what if I repeat this experiment so many times? So let's do it very quickly. So what happens if I repeat this, many times? So what's going to happen? So what I'm going to do is I'm just going to copy this. So you don't have to write the whole thing. I don't need this one. So what I'm going to do is, now let me call this HL, because I don't want it to be mixed up with the other one. HL, okay. Let me see how should I do this? No, I'm sorry. So let's just take this back, heads, because I'm going to repeat this many times. Each time I will have a certain number of heads. I'm going to keep those number of heads inside HL. Okay, so let me run this for J in range, I don't know, 1,000 times. Okay, and then I am going to take this whole thing to the right. So, and then every time this experiment is ending, right? So once I am done with this experiment, I am going to append the number of heads, ranked heads. I hope this is going to work. Again. Okay, I think it worked. Now HL has so if you check HL, the first 10 elements of HL, these are all number of heads. What happened here? Oh, I have to assign every time heads should be empty, right? Yeah, that's what happened here. Okay, yeah. So now number of heads at each iteration is around 65. So what I'm going to do is, because I ran this experiment 1,000 times, what I'm going to do is NumPy mean of HL. This is going to give me a much, of course, what is NumPy, right? Import NumPy as NP. So it is 66.035. Again, mathematically, for these numbers, we found 65. Let me just, this is my last thing, okay, with this question. I know I spent so much time on this, but let's run this for 5,000 times and then see if we can get a much accurate number. So 65.69, which is almost the same with the mathematical expression that we used to find expected number of heads. I hope, again, nobody is going to, I want you guys, I want myself actually to understand, right? So what is actually going on behind the scene? So we don't know what the interviewer is going to ask us. So he might simply be happy with this mathematical expression, or he might tell you that, you know what, can you please simulate this? So if that is a question, we can simulate it. And in our minds, we know that what is happening, right? So even we give the answer in mathematics, right? So we know why that is the case. Okay, so please let me know if you have any questions on this one. Otherwise, I'm gonna move to the next one. Let me check if HL should be heads. Yeah. Yeah, so thank you. You guys point out the mistakes I was making. So thank you for the corrections. Any questions? If not, then I'm gonna move to the next question. Okay, so then let's look at the next one. Let's look at the next one. This is a different question. This is a little bit different. I'm planning to have a couple of more sessions on hypothesis testing AB. So I want to make sure that we all understand it 100%. So without talking too much about hypothesis testing, jumping on this kind of a question, I know it may be too much. But let's see. So I'll try my best to break this question into small pieces, and then we can understand all together. So let's say you are in charge of shipments at an organization, and there are two types of parcels you can ship packages in. So say there is a parcel A and B. So basically you are sending packages in two different ways, let's say. So the way you package them all. So packages delivered in parcel A are damaged during shipment with probability P. And then packages with parcel B are damaged with probability Q. Basically, the packages might be damaged, and the damaging probability for these two parcels are different, P and Q. They might be the same, but let's assume for now, one is P, the other one is Q. Yeah, thank you. Somebody asked me to copy and paste the question in the Q&A session, so I'm gonna do it. I hope you can copy from Q&A. So I just answered to the question. If I can copy and paste the question, I hope you can copy it from there. Okay, so let's continue with the question. Okay, so if that is the case, right? What statistical tests could you use to determine which parcel is better to use? Again, both they individually have these two. They have different probabilities of the packages being damaged. So, what kind of a statistical test you will use to actually determine or decide which parcel is better to use? So, what will the statistical test conclude? Now we are assigning values. If P is 0.4 and Q is 0.6, and let's make this a little bit more close to real case. Let's say I have 200 shipments, and then half delivered with parcel A and half delivered with parcel B. And if P is 0.4 and Q is 0.6, and then what kind of a statistical test you would use to decide which parcel is better to use? Okay, so that is the question. So we are going to try to solve this question together. Okay, so now we are going to compare two parcels. So basically, we are referring to success rate, right? So failure or success rate. So success rate is in this case, let's say in this case, the package is being damaged, right? So we are going to compare these two parcels, their ratios. So in that case, it is maybe good to use two sample test of proportion, right? So we have two proportions, right? So there are two samples of proportions. So we are going to be using two sample test of proportions. So which parcel is better? So at this point, it looks like first is better than the second one because the probability of that being damaged is less than the other one, but maybe these two have equal probabilities. So this is just one sample of that, right? So maybe this difference here is not that big, right? So that is what we want to test. If the difference between these two is not that big, then both parcel A and B are the same, right? But if this difference between A and B is, I'm going to use the word statistically significant, that difference, then we're going to prefer one over the other. Okay. All right. So let's slowly try to solve this problem again together as much as we can. Okay. So for solving this problem, I'm going to be using NumPy. Okay. And I will also use normal distribution. So so you have different options to use normal distribution. I'm going to use SciPy stats. Okay, I will import normal distribution. Okay, so I need these two packages. So let me, these two libraries actually. So let me import them. So now we have two ratios. We have two ratios. So let's just use them. P is 0.4 and Q is 0.6. So I have two ratios. And in the first case, so we were told that we have 100 packages in the second person. And the number of damaged in the first one, let's use X1 damaged, okay? So because damaging probability is 0.4 times 100, so I'm just using numbers here, so 40. So, and then X2 damage is what, 60. Well, once you are given P and Q, you may not need X1 and X2, but for the sake of completeness, I'm putting all the numbers up front so that we can use them. Okay, so let's do this, and we assign the values to our variables. So what are we trying to test in here, right? So what is the goal in here? I have two different kinds of shipments, and then I would like to see if these guys are the same, or one of them has a higher probability of damaging the higher probability of packages being damaged than the other, right? So that's what I want to test. So let's decide on what we want to test. Okay, so I mean, as I see, what is that? So it's up to us how we decide, but because it looks like P is in terms of, again, this is the probability of being damaged, right? So this is what is that? This is up to us how we decide. But what I'm going to do is my hypothesis is that my null hypothesis is that I mean, again, it is up to us whether I can say P greater than Q or Q greater than P. It is just up to us. Okay, it is up to us. But let me do this. Let me do this. I will assume that P is greater than Q. Okay. Again, it is up to us. You can do the other way. It's the same thing. And then my alternative hypothesis is, let's say P is less than Q. Again, you can do the other way too. It's up to us. Nothing will change. Nothing will change. Okay, let me make this as marked down so that it's not going to. All right. Now I have to make a decision on what significance level I'm going to be using. Again, I'm hoping that we're going to have a separate session on discussing each of these things separately, but I'm assuming that you have some knowledge on significance level. So let me use the significance level of 0.05. So what does that mean? What does that mean? To explain this, if you allow me to draw a normal curve. So let me first draw a normal curve and then spend a few minutes on explaining what that means. So for that, I will be importing matplotlib, SPLT. Okay, and let me first import this. So you know that I will be using this to plot. So what I'm going to do is I'm just going to generate some numbers between -3 and 3. Okay, between -3 and 3. And these numbers will be generated by step size of 0.1. So basically -3, then -2.9, -2.8. And then I'm just going to plot a normal distribution randomly. A normal distribution, okay, for these z values. So I will plot. Z is the x-axis, and then normal distributions, I'm using probability density function for z. So for each value of z, I am going to find the density function value from the normal distribution, a standard normal distribution. Okay, that's what I'm doing here. And then let me also label this. Okay, now this is going to work. Okay, so this is my normal distribution. Normal distribution, standard normal distribution with a mean of 0 and a standard deviation of 1. Again, the numbers are changing from -3 to 3. So what I am going to be doing with alpha value is, I am going to find some value, which I will find that value later on. And then I'm going to look for that value on this number line. Okay, I'm going to look for that value. So I'm going to find some value at some point, and I'm going to look for that value on this number line. Let's say that that value is right here. Okay, let's say that value is right here, which is -2.8, let's say. Okay, so if it is -2.8, I am going to find what is the probability that my numbers along this number line between -3 and 3, what is the probability that my numbers are less than this value, which is -2.8? Again, I'm repeating, given this normal distribution and this number line from -3 to 3, if I fix a number, let's say -2.8, and then if you ask me how you found -2.8, I'm going to talk about that, okay? But let's assume that there is such a number that I just fix it and then put it here, -2.8. So what is the probability that my numbers on this number line are less than -2.8, okay? So they are going to be, actually, it's going to be the area under this curve from -3 to -2.8. So that is the area under this curve from -3 to -2.8, right? That area. So later on, what I'm going to do is I'm going to compare that area with this alpha value here. Okay, so that is what I'm going to do. If this area is smaller than this alpha value, then the value that I used, -2.8, remember, it's a number which is very rare to occur. Okay, if the area under the curve from -3 to this number that I picked is, that area is less than this 0.05, that means the number that I picked is some number that is extremely rare to occur on this number line, given this distribution. Okay, so let's now go back. Okay, so I'm sorry, I just jumped ahead, but let's go back and then continue with where we left. So we set alpha equals 0.5. We set our null and alternative hypothesis, and these were the numbers which were given to us. Okay, now the next thing is I'm gonna find the pool. So I will be comparing two proportions. Please, if you don't know, or if you don't remember central limit theorem, again, this is something that we might discuss later with a couple of questions. I know there are a lot of questions related to central limit theorem in interviews, theorem, and approximation of binomial distribution to normal distribution. Now, I assume that we know this topic, okay? Central theorem and approximation is an X of binomial distribution, normal distribution. So if you know these two, if we know these two, then it makes sense to continue with the following equation that I'm going to be typing here. Okay, just 1 second. Let me make this mark down on this one mark. Okay, so there are questions here. So yeah, recordings will be posted at YouTube. Python file. So there is, I'm just typing the Python file now. Okay, is this the p-value that is rare to? So the p-value is the probability of, again, don't please, this is something that we commonly make a mistake. Okay, p-value is not just the probability. P-value is the area under this curve. Okay, p-value is the area under this curve given the number that I picked, right? So it was -2.8. The area under the curve from -3 to -2.8, that is p-value. Okay, that is p-value. Okay, so what I'm going to do is there are two proportions. What I wonder is if one of them is greater than the other. If one of them is greater than the other. So if one of them is greater than the other, what I will do is I will be subtracting one proportion. Let me call it what is that? P, right? I will subtracting Q from P. Okay. I'm sorry. Q from P. So P is the proportion in the first parcel. Q is the proportion of damaged packages in the second parcel. So I am going to be comparing these two, this difference between P and Q. Whether this difference is, I mean, 0 or not. Okay. So if P minus Q is 0, that means P and Q are the same, right? So if P minus Q is not 0, that means I mean, if I am looking for if P is greater than Q, so this is what I will be checking, this difference, whether this difference is significantly different than 0 or not. Okay, so what is 0 in here? For both parcels. Okay, if you assume the damaging ratio is the same. Okay, so imagine that there is this world where both parcel A and parcel B, they both have the equal, what is that, damaging proportions, right? If you take the difference of these two equal proportions, it's going to be 0, right? If you take these two equal proportions, difference between these two equal proportions, it's going to be equal to 0. Okay. Again, if for both parcels, if in that world, which may not be real, okay, if you assume that P and Q are both coming from the same distribution, okay, their difference will be 0. And then if you assume that they are coming from the same distribution, the variance, right? The variance, if you want to, let me type it here. If you want to calculate the variance, if you assume P and Q are coming from the same ratios, okay, same distribution, sorry. Okay, so in that case, what we have to do is we need to calculate or compute the variance or the standard deviation for the pooled packages. In other words, I'm going to pull 40 and 60. I will assume that all these 40 and 60 packages, damage packages, are actually coming from the same ratio of damage packages distribution. Okay, so there is some distribution out there, and then 40 and 60, they both are coming from the same distribution. If that is what we assume, we are making that assumption because we want to test how different P minus Q is from 0, and this is our assumption that P and Q are coming from the same distribution. So in that case, I will have to use, go to the next line. In that case, I will have to use a pooled P, right? P pooled hat. So those who know about hypothesis testing, if you knew the variance of the population out there, you would use that variance, right? If you did not know the variance of the population, which is for most of the cases, we don't know the variance of the population out there, and then we have to make a decision about a sample that we got from the population. In that case, instead of using, because we don't know the variance of the population, we will compute the standard deviation from the sample and assume that that is the same with the population's variance, right? So if you guys know about hypothesis testing using a sample from a population when you don't know the variance of the population, that is what we do. Same thing goes for ratios. So in this case here, what I'm going to do is I'm going to calculate the P pooled hat, which is the proportion of damaged goods for the pooled data set, which is I'm putting both N1 and N2 into the same pool. Okay, so and then I will calculate the variance of that population that I don't know. So I'm using what I know, the sample, to use as the variance of the population in this case. So P pooled hat is X1 damage. So this is the number of packages which were damaged in the first parcel, and then X2 damage. This is the number of packages damaged in the second parcel. And then I find the ratio of these two with respect to the total number of packages. Okay, guys, again, this is the pool of all the packages, and this is the number of all damaged packages. So my assumption here is parcel A or parcel B, the damaging ratios are all the same, coming from some distribution, okay, out there, which can be imaginary. Okay, so given this imaginary distribution, I'm going to compare how different P minus Q is from that imaginary scenario. Okay, if P minus Q is so different from that imaginary scenario, then I'm going to say that, oh, P minus Q is so different from 0. That means P and Q are so different from each other. That means one of the parcel is different than the other parcel in terms of having goods or packages damaged. Okay, so that is the logic. I hope I'm able to explain what I'm thinking. Okay, so this is P pooled hat. So again, remember from binomial distribution and summation of binomial distributions, how we can find variance given P, right? So let me find the pooled variance. It's nothing but using this P pool. Let me use just P pool hat. Okay, times. So basically, remember it is P times 1 minus P, right? Divided by, what's that, N, right? So I'm using this formula here. P pool hat times 1 minus P pool hat, okay, times. Now I'm going to be dividing this by harmonic mean of N1 and N2, okay? 1 over N1 plus 1 over N2. So what is this? I find the P pool hats and then using that to calculate the variance for this pooled scenario. Okay. Okay, this is the variance. Pool hat is not defined because we did not find it. Silence this. Okay, so I found the pooled variance. Now it is time for me to continue with my hypothesis testing. So I need my standard error. Standard error is the square root of pooled variance, right? So if you like, you can simply say pooled variance to the power of 1/2. Okay, so I got the standard error. So basically what I'm trying to do is, remember, standard normal distribution. Z equals X minus mu divided by standard deviation, right? So that's what I'm trying to do here. Right? So instead of mu, I'll be using the P, and instead of standard deviation, I'll be using this guy here, over here, standard deviation. Okay, so let's continue. Now it is time for me to find the test statistics. So T-stat, go T-stat. The number that I picked as negative 2.8. So I'm getting closer to finding that negative 2.8, whatever that number is, okay? So this T-stat is basically this Z number, okay? So instead of X, I'll be putting P minus Q, P minus Q. Instead of X, I'll be putting P minus Q. Okay, let me do it, P minus Q, okay? Instead of mu, I'll be putting 0, because mu is the ratio difference between P and Q, and then mu is what we normally assume that the sample is distributed according to, right? So here, our assumption is P minus Q is 0. That means P and Q are coming from the same distribution. Okay, P minus Q minus 0. And then, of course, I'm going to be dividing by standard deviation, which is SE. I just found it here. Okay, so I got my T-stat. Okay, so what is this T-stat? So let me see how it looks like. Oh, I just found that number that I was talking about, right? Negative 2.82. So I found the number here, negative 2.82. So what's happening here? What did I do? So basically, now this distribution over here is a standard normal distribution. I told you that if you knew about central limit theorem says, given any large number of samples from any distribution, if you sum them up, let's say that is the summation. And if that is the average of those large number of samples, and that if that is the standard deviation of all these large number of samples, so this X minus mu divided by standard deviation, whatever that is always normally distributed with 0 mean and standard deviation 1. Basically, we call this standard normal distribution. So for any kind of context, any distribution, if you have large number of samples, that's where we are going to end up with, okay? So what happened here is, we started with these numbers, right? So we suddenly begin to talk about this distribution. So what is the relationship? So we started with these numbers, and then we say, if these numbers were coming from some population out there where P and Q were the same, right? P and Q were the same, and then if I take P minus Q as the difference between P and Q, if they were the same, their mean would be 0. And this is the standard deviation of the sample I have, right? So this number here is nothing but this Z. That means this number is some number on this number line, and then I have the standard normal distribution for whatever that number is, okay? So that number, T-stat, is one of these numbers on this number line, and I know the value corresponding to this T-stat on this standard normal distribution, okay? So if it is negative 2.82, then negative 2.82, I can locate it on this number line, which is standard normal distribution, negative 2.82. Then I can calculate, okay, what is the probability that I can get either negative 2.82 or any number less than negative 2.82. Because why? Why any number less than negative 2.82? Let's go all the way back to where we started from, right? So I said, I'm testing if P is greater than Q or if P is less than Q. Now I took P minus Q. I took difference of P minus Q. if P minus Q is a very small number, okay, if P minus Q is a very negative number, that means Q is greater than P, right? That means Q is greater than P. And then if I go towards left, Q becomes even more than Q. So Q becomes even more than P. P minus Q. Sorry, guys. This is difficult to sometimes explain, okay? So P minus Q is what I'm looking at. If P minus Q is a negative number, then, right, Q is greater than P, right? So that's what I'm trying to understand, whether Q is greater than P or P is greater than Q. If P minus Q is negative, right? So it's right here, negative 2.8. Given my samples, that's what I found, okay? So if I go towards left, then P minus Q will be even more negative and more negative and more negative. So this number line is representing P minus Q. If P minus Q is 0, that means P and Q are the same. That means they are coming from the same distribution. If P minus Q is positive, that means, it's likely that P is greater than Q. What I'm trying to see here is if P is less than Q. That is my alternative hypothesis. That is my alternative hypothesis, okay? So the more I go towards left, the more I get closer to my alternative hypothesis. The more I go towards left, the less likely that P minus Q being negative is happening just by chance. Okay, let me write what I'm saying here. The more I go towards left on the number line, the less likely that P minus Q less than 0 happens by chance. Okay, I hope this part is clear. There are some questions here. Could you? Sure. So there are some people leaving. Thank you. There is a mistake in the pool. Dividend by n should be 1 over m1 plus m2. Let me see. This part, I think this part is correct. So this part is 1 over m1 plus n2, Gayatri. But this part is when you calculate the pooled variance. I think this is the formula. I can check one more time. I cannot check it now, but I think that is the formula. Okay, guys, we are very close to be done. So I tried to explain what this T-stat means, and I hope it is not so confusing. So now we got the T-stat value. So what we are going to do is we are going to find the area under the curve, starting from left towards that T-stat. So all the way to T-stat. So I'm going to find the area under this curve coming from negative infinity up to this T-stat. By the way, this is called what we are doing right now is a one-tailed test. Why one-tailed test? I'm only focusing on this left part because this is what I'm testing. If P is, what is that? If P minus Q is less than 0, that's what I'm testing, okay? If P minus Q is, that's my alternative hypothesis. That's why less than is showing towards left, okay? So that's why I'm focusing on the left tail. Okay, so it's time for us to find the area under the curve up to T-stat. So let's find it. P value is, again, nothing but the area under the curve from negative infinity to up to T-stat. It is nothing but the normal distribution's cumulative distribution function value. Cumulative distribution function values, I'm adding up all probabilities starting from negative infinity up to T-stat. Basically, I give we are just taking the integral, right? Integral of -3 to T-stat, integral of probability distribution function from -3 to T-stat. Okay, cumulative distribution function. And this is going to be tested T-stat. All right, nice. Okay. Now, just be careful. Okay, just be careful. If our one-tailed test was not left side, but right side, if it was right side, then I would be subtracting this from 1. So don't be confused, okay? Because I'm curious about area under the curve. The whole area under the curve is 1. if it was a right tail test, I would subtract everything from, so this cumulative distribution function gives me, this guy gives me the area under the curve starting from left. So if you are doing right tail test, in other words, instead of negative 2.38, let's say your t-stat is 2.38, then the area cumulative distribution function CDF is going to give you the area under the curve all the way to 2.38. But you are focused on this small area here, right? Then you need to subtract from 1. Okay, if it was right tail, because it is left tail, we don't need to subtract from 1, because again, coming from negative infinity to negative 2.30. Okay, I talked too much, so let me find p-value. So let's see what p-value is. P-value. So 0.02, what was our alpha? 0.05. So if, let's write this in terms of a code. If absolute value of my t-stat, let me write this later. Let me write this. If p is less than or equal to my alpha, okay, print reject the null. Right? So our p-value is less than or equal to alpha. What is alpha? 0.05. So the area under the curve is representing, again, how likely that p minus q less than 0 is happening by chance. Because the likelihood of p minus q less than 0 happening by chance is even smaller than 0.05. That's what is happening here, right? Smaller than 0. That means this, what we found now, is something significant statistically. It cannot happen by chance. It is something statistically significant, because what we found is less than 0.05, which is our critical value. So in that case, we're going to reject the null. What is null here? P is greater than Q. This was our null hypothesis. We are going to reject this. This doesn't mean that P is less than Q. It doesn't mean that P is less than Q. It means I have enough evidence to reject null hypothesis. That's it. I don't have evidence that P is less than Q with certainty, but I have enough evidence that I can reject null hypothesis. That doesn't mean that P is less than Q. I hope this part is also clear. Let me just do a little bit of coding. I know that it's already too late, so let me check if we have any questions. Okay, so we don't have any questions. All right, then let me stop here. Okay, let me stop here. I have another question that I would like to work with you. This is more comprehensive than this one. It's going to take longer than this one. So what I'm going to do is I'm going to add 2 more questions next time, and then we're going to have our 4th session. I hope I can get an interview question regarding hypothesis testing, so that blending this one with hypothesis testing, and then this question is about A/B testing, it's going to give us a much clearer idea about what we are doing in terms of calculating Z test and DT test, comparing them, what is p-value. So I hope it's going to be clearer when we solve 2 or 3 more questions. Okay, let me stop here. It's already 1 hour. Thank you for listening, and please don't forget to post your reviews about these sessions. Let us know what you think. So this will help us to get motivated and then correct our mistakes. Okay, thank you for listening, and take care, guys. Bye.